So we're switching gears and going to the data format session and start with the HDF5 group. Dana.
I'm Dana. Is this on? Is it working?
No, right now.
All right, is that working? Okay, great. Hi, I'm Dana Robinson. I'm the Director of Engineering at the HDF Group, and I'll be talking about crash-proofing HDF5. So first, some acknowledgements. I did not do most of this work. I'm just the messenger. This was really mainly put together by Neil Fortner, our Chief Architect, and Valen Choi, Matt Larson, and Glenn Song. So we'll go over a couple of things. We'll talk about, we'll have a very quick overview of HDF5, people who really don't know that much about HDF5. We'll talk a little bit about why crashes can corrupt HDF5 files. And then we'll talk about the crash proofing feature that we've been developing. So I don't want to spend a lot of time on what HDF5 is, but people do need to know some stuff in order to understand the feature. HDF5 is a binary self-describing open file format. You can think of it as a file format in CAN. And so it's basically the main objects are groups, which are you can arrange hierarchically to organize other file objects like groups and datasets. Datasets are n-dimensional, strongly typed arrays of a single type, and you can attach attributes and things to them. Now, the important thing is that just like in a regular file system, there's things that you see, like the groups and the data sets and the files and the directories in the file system, but there's a lot that you don't see that's hidden under the hood. There's a lot of file metadata that we have inside there, and this is used to locate stuff in the file and describe it. And so if this becomes corrupt, then your file becomes corrupt and you can't read it or you lose data. Another thing that's important to understand, and I get this question sometimes, so I'm putting it here because we need to think about this when we're thinking about crash proofing, is that there's no server. There's not, HDF5 is not a DBMS. It's just simply a library that is linked onto your application. And the reason I'm belaboring that point there with that process is that when you kick the power plug out of something or your process crashes, everything that's volatile in that process boundary is gone. And so as far as the internals, like the only thing you really need to know for the purpose of this talk is that every time you open a file, there is a per file metadata cache that is created inside the library. And we're pretty smart about understanding when a file has been opened multiple times. We actually have some platform-specific code that tries to peek at the file system stuff to guess when we've reopened a file, even if you used it through a symlink. And so you get one metadata cache per file. And this is not a write-through cache. So when the metadata cache, when the library writes some metadata into the cache, it does not go immediately out to the disk. It just hangs out in there until something triggers that being flushed to the disk, like if something's been closed or the cache gets full. Or you call H5F flush or something like that. So now, why is it a big problem when a writer crashes? So the first problem is that you have distributed volatile state, that whenever you're writing to an HDF5 file, your state partially exists on the disk in the physical file, but also partly in the volatile metadata cache that is inside the library. And so when the power plug gets kicked out, everything that was volatile is gone forever and you will never see that again. Now you may be able to fix that. The file format is open, there's no automated tools for this, but that's really, really, really difficult. It may be impossible depending on what has been lost from the file. So another problem is that when this happens is that you can wind up with inconsistent state. So if you have something like a tree where you have a node A that refers to some other node in the file B, and A was written out, but B resided in the metadata cache, what will happen is when you have that file and the library tries to parse that and try to find a data set that's located inside there, then A will point to garbage, and when you try to resolve that garbage and turn that into a B tree node, it errors out or crashes. So the result, lost data, corruption, or crashes when reading corrupt files, wasted time and money. Now, I do want to emphasize that this does not make HDF5 a bad format, right? This is the case for anything that is using caching and does not have like a journaling system or a log system or something like that. So the proposed system that we've come up with in this crash proofing feature is to use a write-ahead log. So it's simply a log of batched metadata writes that ensures that metadata that's written to the actual file is in a consistent state and it can be replayed after a crash. And if you look at our really simple cartoon here of what this looks like, the metadata cache is something that exists in the library, the IO and VFD layers. The VFD is virtual file driver. It's a pluggable system for doing I/O. You can have an MPI VFD, for example. And then the write-ahead log module is the new thing, all the yellow stuff, and then that write-ahead log file, which we also write through of the VFD layer. So how does it work? So metadata normally accumulates in the cache as usual. And when metadata is evicted because the cache got full or something got flushed or got closed, that gets written to the write-ahead log. And then when it's time to flush, there's two kinds of flushes. There's a log flush operation, and there's a checkpoint flush operation. And they're pretty similar, but they differ in that the first one only writes to that write-ahead log, and then the checkpoint flush operation goes to the file as well. So log flush operation flushes the entire metadata cache contents to the WAL file. It does not write to the HDF5 file. It creates a consistent metadata checkpoint. So if we go back and look at this here, what we're doing is we are, where'd it go? Hang on. There we go. What I see here is a little different. So what we're doing is we're serializing that metadata cache out in a coherent way into that WAL file, so that when you kick the plug out, it actually is restorable. So that creates that consistent metadata checkpoint in the WAL file. So if we replay that, we can patch up the file. That's configurable as to when this happens. You can use the amount of metadata written, time interval. We have a flush API call that we'll be adding. Then the checkpoint function is a little bit different. It first performs the log flush, dumping the cache to the WAL, and then it does it writes the data from the WAL to the HDF5 file. So basically, it goes through, it pulls all those regions out of there, and we'll look at the file format in a second, and it patches up the HDF5 file, and then truncates the WAL so that doesn't grow infinitely if you have a metadata heavy thing. So we'll skip over the flowchart in the interest of time. The WAL file, it's really simple. It's a simple, we have a super block, and then every time something is written into it, it's just a simple offset and length, and then the metadata block itself. And there's a special form of the block that can be read as a WAL, as the log flush marker. And essentially what you're going to see as you're doing this is you're going to have the WAL operations are much more lightweight than writing onto the HDF5 file. And so you should have a lot of those, and then you get to the point where you want to actually like sync and write to the HDF5 file. And then that's the more expensive operation. And then so that happens at a slower cadence than the log flush files. So the scope of this is only metadata. This is not about raw data. There's other ways that would be really expensive, and it's easier to control that with like actual flushes and things like that. We are not going to be supporting variable length data and references, even though if you know about HDF5, those are stored as metadata, which was a bad idea. But we're not going to be supporting those. And it will work with parallel HDF5, which is our primary use case. There'll be a single writer that writes out to the WAL, and then all other MPI processes can read from the WAL. And we already have cache synchronization, so we can just leverage that to handle all of that. Another feature that we have in HDF5 is the single writer multiple readers function, and functionality. That's where you can have one writer, and then you have a bunch of reader processes that are reading from that file. And we have set up flush dependencies in the cache to make sure that we never have that A-B problem that we had earlier, and that only works for data set appends though. It doesn't. The whole file, like creating groups and things like that, is not supported under Swimmer. But this is compatible with this WAL file, and then it also supports page buffering and metadata accumulators. So recovery. So when a crash occurs, we can have file recovery happen in two ways. One is automatic. So when we open up the file, we will write the location of the WAL file into the file's super block and remove it when the file is properly closed. So if we find a file that has a WAL message in it, we can go open that file if it exists, and we can find it, and then do the repair automatically, and that's controlled via a property list. You can turn that on and off if you want. But then there's also an H5 repair utility that will include that will fix it for you, and you can specify a different location for the WAL file and things like that. And the algorithm is pretty simple. You look through to find the last full checkpoint in the file, and then from that you start pasting in and patching in the HDF5 file until you have a coherent file again. And then you remove the super block message, and you truncate the file back to the super block message in the WAL, and delete all the entries. And so if you have read-only access, it's a little different because we can't patch the file up. So instead, what we'll be doing is we'll be creating little stub entries in the metadata cache so it knows where to go get the pieces of it. So we have new APIs to control all this because everybody loves when we complicate our API with new API calls. So there'll be an H5P set wall and get wall functions that actually go in and set that functionality up. And then there'll be a way to set up the H5P set wall auto recovery, whether or not you want it to auto recover if it opens up a file. And then you can also custom do a wall flush if you need to. So in order to support this feature in your application, you really don't need to do very much at all. The only thing you would really need to do is just use the H5P set wall function at the beginning, and it would start using it, and you can set all the parameters in it. And if you don't want to do automatic, if you don't want to change the frequency at which it flushes, then you can just get away with that. So it should be pretty easy to use. So in summary, what this will give you is, with the crash proofing feature, corrupt files should be a thing of the past. You should not have to ever have a file where you've lost a bunch of data and now you can't open the file at all, even with this feature working. You will be less likely to use data after crash, but it's not an entire guarantee that you will never lose file data. If you get caught in between the wall flush operations, the log flush operations, then you could lose some of that data, but that should be minimized as long as that frequency is at a reasonable cadence. So the current status of this is it's currently at the design stage. We have an RFC that we've put out that basically iterates, that talks about everything that we have here, including internal details. We're looking for funding to complete the feature. And then we've done some work to simulate the I/O loads that we expect from this. We modified one of the VFDs. I didn't have time to put that. I didn't want to put this in here in the interest of time, and the data are difficult to interpret. But we see that it's maybe only a few %. So it's not a really big load, as long as you don't have a very metadata-heavy workload. If you're doing something where you're creating a lot of groups, like we're trying to do systems biology and like create a lot of links and stuff inside of a file, that maybe is not a good candidate for this. But a lot of like HPC workloads or something where you're collecting a lot of data from an instrument, this should really not add too much to your workflow. And then shameless plug, we are a nonprofit organization. If anybody wants to come talk to us about things like priority support contracts or working with us on proposals for grants and things like that, we're always happy to talk to people. And that's pretty much what I have. Also, as an aside, if anybody wants to talk about machine learning I/O patterns and has insight into that, I am 100% interested in talking to you at some point during this conference because I'm really interested in hearing what people's experiences are.
Okay, we have time for 1 or 2 questions.
So thanks for an interesting talk. Not on machine learning. I wonder, did you consider, and would it be possible or would it help to use something like a transaction mechanism? So my immediate instinct is write new metadata into the same HDF file, and when it is properly flushed, just flip 1 bit in atomic fashion, saying all readers that from now on, old metadata is obsolete, using a new one. In that way, it seems you would always have a consistent metadata in an active state, no matter what happens, like in databases.
We've thought about doing things that are more complicated like that, but again, we have limited developer resources, and our main interest is getting something out that is simple, lightweight, and solves 90% of the problems. And for a lot of people who are doing something like if you're writing out in some HPC application, you're writing out checkpoints, and you don't want to have to throw the entire multi-terabyte file away after there was a crash after 20 hours of operation. This saves you from that you can then be guaranteed that you can restart from that checkpoint and there won't be a corrupt file. And I think that pretty much gets us there. But yeah, we're interested in thinking about more complicated solutions like that, but I think this is really scratches a lot of people's itches. Without a lot of work. Yeah.
Okay.
So if I understand correctly, the wall file needs to be, imagine a system where you have several writers using MPI-IO. Mm-hmm. This means the wall file should be accessible and writable from any of them.
Yes.
which
Well,
gives
I mean,
us,
it doesn't need to be writable from any of them. I think it just needs to be readable from any of them because you have a single process.
yeah, but it,
So you
it
would-
needs to be accessible. So it creates some extra constraints on the file system. So the solution suggested by the other guy who asked the question seems to make more sense to me than.
Well, there's only one process that's actually writing to the wall file.
Okay, it's
Yeah.
done by only one, but
Only
it,
one.
it cannot be done on a local disk to improve performances and having some some scratch
Sure.
space. But then the other
Well,
ones,
I mean,
I
well,
don't
okay.
have access to it.
Yeah, then I guess if you did that, then the other processes would have to read from it.
Yeah.
Yeah, we'll have to see. I mean, this is a feature that has not been fully implemented yet, right? We've just done some testing. So how it will actually look and work in practice may change. We've had a bunch of things like that happen with like the subfiling feature that changed over time as we developed it. So we will not be blind to HPC use cases since that's really our primary concern for this.
Okay, I guess we have to shift that discussion also to the next break.